Let's do a couple of equilibrium calculations with solubility and the common ion effect to demonstrate how this common ion effect suppresses dissociation just like it does with buffers and the dissociation of an acid. So if we're going to calculate the molar solubility of calcium phosphate using the following KSP value, let's first do it in a pure solvent to show what our solubility is. So calcium phosphate. Calcium has a 2 plus charge, phosphate has a 3 minus, so we'll have 3 calciums and then 2 phosphates in each formula unit. Well, this is going to give us a form of M3X2. As we discussed in the previous video, it matters what the ratio is in our formula unit of each one of these. And so it's going to give us some stoichiometry equivalents here where we have 3 calcium ions that are going to dissolve aqueous solution. Okay, best there. And then 2 phosphate ions in aqueous solution. Remember, our salt here is a solid on the left side of our expression. We're dissociating. And the equilibrium constant of this is KSP. Well, for our ice table, our initial concentration of salt doesn't matter because it's a solid, and it will not appear in the equilibrium constant expression. We start with nothing for each of these guys because we are dissolving in water initially, pure water. Our change, though, we're going to gain 3 times as much calcium as we dissolve calcium phosphate, and we're going to gain twice as much phosphate as we dissolve for calcium phosphate. So X is still the molar solubility of calcium phosphate, but we have multiple equivalents that we have to take into account. So we gain 3X calcium, 2X phosphate at equilibrium. So how does this look in our expression? Well, we've got a KSP that we said was 1.0 times 10 to the minus 25, very, very small number. And we broke up into calcium. How many of them? 3 of them, so that gets cubed. Phosphate, how many? Well, we're going to get 2 there for phosphate, 3 minus there. 3 calciums from the 3 minus charge of phosphate and 2 from the 2 plus charge of calcium, and that's from our balanced equation and forming the equilibrium constant. What does that do to our calculation? Well, now we're going to cube 3x and we're going to square 2x. So that gives us 9x cubed times there 4x squared, and that's going to equal 108 times x to the 5th. Okay, and all equal to our equilibrium constant there. So finally what we're going to get is divide by 108 and then take the 5th root, and we're going to get 3.92 times 10 to the minus 6 equals our solubility of X. Our concentration of calcium would then be equal to 3X, and phosphate, PO4 3 minus, that concentration is equal to 2X there. Okay, so 3.92 times 10 to the minus 6 is our solubility. Now, what if we throw that common ion in there? What happens? So same expression, calcium, 3 of them, phosphate, 2 of them, we dissociate 3 calciums, 2 phosphates, and we start now, instead of starting with 0 like we did without the common ion in place, we've actually got a solution that we're starting that is 0.25 molar in calcium bromide. We don't care about the solid, but we do care that there's already 0.250 molar calcium in play. If we were looking at bromine, we'd have to multiply that value by 2 because we've got 2 equivalents in the salt. We're not, and calcium bromide is as strongly soluble, so it should not affect the equilibrium very much. And we start with no phosphate. So we do have a common ion initially that we have to take into account. As we dissolve, we're going to get 3x, 3 equivalents of calcium for every 1 calcium phosphate, 2 equivalents of phosphate for every 1 calcium phosphate, And at equilibrium, we're going to have 0.250 plus 3x for calcium. There's where we're different than last time. And then just 2x for phosphate. So again, we're setting up our KSP expression. And we are calcium to the third. We are phosphate squared. And our values here, for calcium, we really only need to consider 0.250 to the third, because that 3x, because our value of concentration here is so much larger than our constant here, and last time we even calculated x was times 10 to the minus 6 here in a pure solution. So since that value is so small, look how it lines up. This is our given molarity. This is our projected x value. 3 10 to the minus 6 is going to be somewhere out here. And so we're so much smaller, 3 or more sig figs different and smaller than our concentration, we can ignore that x as it compares to our 0.250 molar. So we drop that out. That simplifies our expression a little bit, but we're still left with 2x squared for phosphate. Multiply these together, we're going to get 0.015625 when we cube out 0.250, and then we get 4 times 4x squared. And then we can divide both sides by 0.015625 and by 4, and we're going to get x squared equals some value here. Oh, I didn't write that one down, but you can get that one. And then let's just go ahead and take the square root, and we get 1.26 times 10 to the minus 12. So that part for x squared, just divide both sides by 4 and by 0.015625 before you take the square root. No problem there. You can do that in the calculator all in one step. And when you do that, you get the molar solubility is 1.26 times 10 to the minus 12. So comparing that to before, where we were at 10 to the minus 6 with no common ion effect, versus where we do have the common ion effect, that's a big difference there. 10 to the minus 6 versus 10 to the minus 12. We've suppressed ionization a whole lot by adding in that common ion.